Now, as you understood now, that u is a state function, right? We discussed that u is a state function, and we tell that delta u, that is the change in internal energy, depends only on the final and the initial states, that is uf minus ui. Now I can think of an infinitesimal change, right? An infinitesimal change in the internal energy, or we can call it like a differential change in internal energy, which is denoted by du. Now, if du is a differential change, then if I integrate du, so it's a total differential, and if I integrate du from states ui to uf, basically the integration will basically give me uf minus u, right? Now this du is called a total differential or an exact differential. This is a very important, so the state function property is very important in thermodynamics, because it gives you, so since u is a state function, you can write it as a total differential or an exact differential, and these exact differential properties exploited at various times and used at various times, and this becomes very, very important in thermodynamics, right? So it becomes very important to understand, or it's a very useful tool. Which, if you have a state function, you can express it as a total differential, and you can, using this total differential or exact differential properties, you can derive many useful relations that you will see later, right? So another thing that I want to tell you, that you have to be very careful in thermodynamics about units, right? For example, in general, we will use throughout this course SI units. So SI units are like joules. Say for example, internal energy, the SI unit of internal energy is joule, and joule, as you know, 1 joule is basically equal to 1 Newton meter, right? Joule is the unit of energy, joule is the unit of work is like force times displacement, and force has a unit of Newton, and you have like for length, for distance, the unit is meter. So 1 Newton meter is 1 joule, and 1 Newton is nothing but 1 kg meter square per second square, right? Because it comes from Newton's law, force equal to mass into acceleration, right? And then heat and work, right, have the same unit as energy, as energy, and what is the unit? Joule, right? So heat, the unit of heat is joule. We will take the unit of work as joule. So basically, all of these units we have to be very consistent, and we are using SI units. But many a times in problems, sometimes people use this British units, and sometimes they use this CGS units, so-called CGS units. For example, calorie is still a very popular unit for heat input, right? And 1 calorie is defined as the heat input to raise the temperature of 1 gram of water by 1 degree Celsius, right? So it's 1 calorie is the heat input to raise the temperature of 1 gram of water by 1 degree Celsius. And 1 calorie is nothing but 4.184 joules, right? It's an exact conversion. You can think how is it derived. You think about it a little bit, that it's 1 gram of water, 1 degree Celsius, you want to raise it by 1 degree Celsius, and get and what you define is 1 calorie. And you will see later why this is an exact conversion, or you can yourself also work it out. Now, electron volt is another very popular unit of energy, and electron volt is basically, when you express it, we generally express energy per kg or energy per mole, but if we want to express energy per atom, then electron volt is the unit of choice. And electron volt is the kinetic energy acquired by an electron that is accelerated from rest to a potential difference of 1 volt. As you can see, 1 electron volt is basically energy per atom. So to see 1 electron volt and what is the relation between electron volt and joule, you can understand that there is somewhere Avogadro number coming in, because 1 electron volt equals to 0.16 and 10 minus 18 joules, right? So it is the energy acquired or kinetic energy acquired by an electron is accelerated from rest through a potential difference of 1 volt, right? And if the relation between electron volt and joules is this, it is like 10.16 and 10 minus 18 joules, or 1.6 and 10 minus 19 joules, right? And we also have discussed this molecular interpretation of internal energy. But one very interesting thing that we haven't discussed is, if I have this microscopic or molecular level interpretation or understanding of internal energy, then is it possible to use or find some average energy and find u in terms of that average energy? And this average energy is basically coming from statistical mechanics. Okay, so it comes from statistical theory of matter, and where we are describing matter in terms of particles. Remember, in thermodynamics, that's a very interesting thing. In thermodynamics, macroscopic thermodynamics, we use properties like pressure, volume, temperature. So, for example, volume, we think of 1 liter of water. We don't tell that 1 liter of water contains how many molecules of water and how are each molecule behaving, of water behaving and stuff, right? That is not impossible to describe. But we just tell 1 liter of water and immediately people will understand what I am asking for, right? It's all a macroscopic description of matter, not really molecular description, because if it is a molecular description, as you know, say for example, I have this 1 mole of helium atoms enclosed in a container, okay, and this is a 3-dimensional container, so it has a volume, and we have 1 mole of helium atoms. 1 mole means Avogadro number of helium atoms, right? And this is a monoatomic, helium is a monoatomic gas, and it is enclosed you can liquefy helium, but we are assuming that it is in a gaseous state. Currently, we are considering it in a gaseous state, and you can liquefy helium at a very low temperature. But here we are looking at it as at a room temperature, and we are telling that this monoatomic gas is enclosed in this container which has some volume, right? Now, if I have to describe each atom in this monoatomic gas, then basically I have to know the position of each atom and the momentum of each atom in this 3-dimensional container. Now, if I want to know the position, as you know from 3-dimensional coordinate geometry, you require to basically specify 3 coordinates, right? X, you have to specify x for each molecule, you have to tell, or each atom you have to tell x, y and z. Now, if I tell momentum, let us assume that all helium atoms have that's a fair assumption that all helium atoms have the same mass, right? And we are telling that if it has the same mass m, then I have to specify the momentum. So, momentum basically, or if I tell momentum per unit mass is, so let's call it momentum per unit mass, which is basically the velocity. So, we have the position which is x, y, z, the 3 coordinates, and you have momentum per unit mass which is like Vx, Vy and Vz. So, if you have 1 mole or Na, which is Avogadro number, 1 mole of He, which is equals to Na atoms of helium where Na equals to 6.023. As an approximation, I am taking 6.023, then but 3, there may be some more values in the, you can go to some 4 or 5th or 6th decimal places, you will have some more numbers. So, I am just using up to 3 decimal places, 6.023, then but 3. Now, you have these many number of atoms of helium in this box. Let us assume. Now, in this box, for each of these atoms, I have to define these 3 positions, right? 3 positional coordinates and the 3 components of velocity like Vx, Vy and Vz. So, basically, I require or it requires. It's basically, if I want to describe it at the molecular or microscopic level or the atomic level, basically we have to describe 6N, 6Na, basically 6Na, 6Na positions. So basically like 6Na variables, right? So you have 6Na variables to describe, are required to describe 1 mole of helium at some temperature right? You require 6 NF variables, which is like a very huge number of variables. On the other hand, if I just tell 1 mole of helium, the chamber contains 1 mole of helium, it at certain temperature T, I specify the temperature, I tell the mole number, right? How many moles of helium are there inside. I can also specify the dimensions of the container. Once I have done that, that's good enough. Means I don't really require this molecular level description of helium. Like if I require such, it is impossible to describe, because it's like you require to know the instantaneous position and velocity of 6.023 into 10 power 23 atoms, which is it's impossible, right? So that is a problem. But this basically gives you one very interesting idea. So if you see, these atoms are basically moving around, right? And it has this something called translational kinetic energy. So for each atom, I can tell of mass m, the translational kinetic energy is nothing but half m Vx square plus half m. See, the Vx, Vy, Vz can be different for each atom, right? But basically you have like Vx for all these Na atoms, Vy for all these Na atoms, and Vz, some values of Vx, Vy and Vz. So basically if I know that, then I can write these are my, this is my translational kinetic energy, right? So basically what I am trying to say is that each of these atoms will have this different degrees of freedom, like 6 degrees of freedom if I tell, and it can be like more degrees of freedom even. So if I think of like translational kinetic energy, but for example, if I take a here we are talking monoatomic, but if I think of diatomic molecules like hydrogen, or if I think of a water molecule, right? Water molecule contains H, right, and 2H and 1O, right? So 2H and 1O, and if I tell that, see, there are so it can basically rotate, right? It can basically rotate. Then on an average, I can tell that about some axis, and I know the moment of inertia. So for example, I, then it will be like we are adding another term. It's the rotational kinetic energy. It's half I omega square, where omega is the angular velocity, right? So you have half I omega square. So this is called the rotational kinetic energy. Now another thing, if you assume these atoms are interacting, and then you can think of these atoms are like balls. You can assume these atoms as like balls, and they're connected by springs. And say for example, as you can see here, this is a plot of a potential energy, and we are telling that at a given temperature, R naught is the equilibrium, right? R naught is the equilibrium distance between two atoms. So R naught is the equilibrium at a given temperature distance between any two atoms, means equilibrium intermolecular distance or interatomic distance. But see, at a given temperature, at some temperature, there will be always these atoms, they will always be displacing from their equilibrium position, slightly displacing from the equilibrium position. Say for example, they are displaced by say R0 plus x or R0 minus x. Now that is so, and spring and you know that this is a spring and these are like two balls, and if you look at the restoring force, for example, and you are thinking of now a simple harmonic motion, right? So about the mean position, so about the mean position you are displaced by an amount x, so you have half kx square, where k is the spring constant, k is the spring constant, and it is related to the bond that forms between these atoms, right? The spring represents a bond between the atoms, right? So k is related to the bond energy. So k is the spring constant. So if you can see, then there is a vibrational kinetic energy. So all these things basically constitute the degrees of freedom at the microscopic level. Now, at the microscopic level, from the classical mechanical point of view, so again, you have also potential energy at the molecular level, right? If you have an ideal gas, then the potential energy is not there because there is no interaction between the gas molecules. But if you think of a real gas, or if you think of a condensed matter, means condensed phases like solids or liquids, then you are having interactions between atoms and molecules which give rise to different types of bonds, right? Ionic bonds, covalent bonds, and metallic bonds. And say, for example, in ionic solids, you have, say, like sodium chloride, you have sodium ion and chloride ion. One is positive and another is negative, and there is a Coulombic interaction, right? And electrostatic interaction between these ions, right? So if you think of example, one example is like NaCl. So you have like Na plus ions and Cl minus ions, and then there is a electrostatic interaction, or Coulombic interaction. Again, bond energy. So there are different types of bonds that can form, like ionic bonds between ionic solids. Then there can be covalent bonds, right? Where you have all these different types of hybridization, and say, for example, bonds between carbon and hydrogen, and carbon and carbon. So, or polymers, and then basically you have metallic bond, like in aluminium. Say, for example, in aluminium, all electrons are delocalized. So basically, atoms are the atom cores are embedded in a sea of electrons, right? These electrons are delocalized. So you form something called a metallic bond. So in each of these bonds that form, again, I am not discussing this. This will be discussed in some courses on physics of solids. Okay, the details of it will be discussed. But I am telling that this will give rise to this bond energy, and this bond energy again can have, it can be a very complex polynomial. You can represent with a very complex polynomial or some function. Now, all of these are happening at the microscopic level. But if all of these are happening at a microscopic level, for example, for a monoatomic gas, I can tell you that if we apply an equipartition theorem, which is coming from classical mechanics, what it states is that if you have an assembly of particles that are in equilibrium at a temperature T, that means that are in equilibrium at a temperature T means the mean temperature for this assembly of particles is T, right? The temperature is T. It is held at a fixed temperature T. Everywhere the temperature is same. The average, then in such a case, the average or mean value, right? The average or mean value of each quadratic contribution. Now, quadratic contribution to energy is something like I omega, half I omega square or half mvh square. This is like a quadratic contribution. So, each quadratic contribution, right, it can be from these different types of kinetic energies, and also it can be from potential energies, right, because if there is interaction between the atoms or molecules. Now, all of this, so for example, if I take a monoatomic gas, ideal gas, and we are talking about monoatomic, so you are not considering any rotational kinetic energy, and there is no interactions, and there can be some vibrational kinetic energy, but assume that it's mostly translational kinetic energy. Then, because you cannot have a vibrational kinetic energy because there is no bond formation or no interaction. So as a result, you have only the translational kinetic energy, and translational kinetic energy means there are 3 degrees of freedom, right? Vx, Vy, and Vz. So each of these, right? Each of these quadratic contributions, the average or mean value of each of these quadratic contributions for all these atoms is the same and is equal to half kBT, right? Where kB is the Boltzmann constant, and Boltzmann's constant is nothing but universal gas constant, gas constant, which is R. Sorry for the mispronunciation. So the universal gas constant R divided by A, N is the Avogadro number, which will basically be KB, and KB is Boltzmann's constant. So it is, as you can see, Na is the number of atoms. So KB is 1.38 into 1.3 joules per Kelvin, and it's also basically per atom, right? For example, R is joules per mole Kelvin, and this is like KB is joules per atom Kelvin, right? So you have KB, which is joules per atom Kelvin, right? Now you have 3 quadratic terms per atom in a monoatomic gas, and so if you add them, then you see the mean internal energy per atom for this monoatomic ideal gas is 3 by 2 kB, right? And then if you have total 1 mole of atoms, which is like the Avogadro number of atoms, right? This Avogadro number of atoms per mole, then we can write which is like the molar internal energy is equals to Um0. So this is Um0 is the molar internal energy at T equal to 0 Kelvin plus 3 by 2, and 3 by 2 kVt is per atom, right? So 3 by 2 into Na into kVt, and Na into kV is nothing but R is the universal gas constant, and so you get Um0 plus 3 by 2, right? So that's your internal energy of a monoatomic ideal gas, which has 3 degrees of freedom because there is no interaction between the atoms. So you have 3 degrees of freedom because of the translation of kinetic energy, right? If you think of a molecule, say for example a diatomic molecule which has also this rotational kinetic energy, then you add another half kVt. Now if you also consider vibrational kinetic energy, you can add half kx square. So it can become like 5 by 2 kVt. In some cases it can come like, if you also consider quadratic terms that come in the potential energy, it can be like 3 kVt or some kVt, right? So basically per atom the mean value, right? And it comes from equipartition theorem of statistical mechanics, right? Now note that for condensed phases, whether it's solid or liquid, the interacting atoms, the potential energy of the interacting atoms always have a contribution. And for example, in ionic solids, it's like Coulombic interactions between the ions, and then there is metallic bonding in metals. And but one thing to remember, it's not very easy. Say for example, there are some simple potentials that can describe interacting atoms in real gases. However, interactions at the molecular level become very, very complex when you consider condensed phases. This is something that we should always take a note of. Okay, so that's the idea. So again, I go back to the first law, and because I want to use this definition of internal energy and I want to incorporate it into the principle of conservation of energy, right? So what it tells is that energy can neither be created nor be destroyed, right? There are various forms of or various restatements that we can use of the internal energy, right? So energy can neither be created nor be destroyed, but can be transported or converted from one form to another, and the total energy unit of the universe is constant. So there are many ways of restating the same, right? This principle of conservation of energy, right? And if we know that, then there is something very interesting that can be written. We all know, but I want to write the differential form, and I want to tell, because I have already defined something called an exact or total differential. I have told that if you have this total differential or exact differential, you can integrate between initial and final states, right, without thinking of the path, right? I haven't defined in exact differentials. I will come to that, and I will also give an example of what is the difference between inexact and exact differential, because in an exact differential depends on the path. But before all of these, I have to first restate the first law of thermodynamics in a simple mathematical form. So remember, in these cases, so basically there are various books like I have mentioned, right, at the beginning of the course. Say for example, the book by Richard Swallin that you can use as a textbook, and then book by Gaskell, and then Robert D. Hoff's book, and there are various other books that are there. And each of these books use different sign conventions when it comes to stating the first law, right? So sometimes we use a convention, we use different conventions. So sometimes you will see, I'll come to that. So here what convention we are using is very simple. So as we know now the molecular interpretation of internal energy, so we will try to be as consistent as possible, and what we are telling is, if there is a heat input to a system, then basically you are adding to the internal energy of the system, right? You are increasing the internal energy of the system. So as a result, heat input to a system is positive. Similarly, if I am doing some mechanical work on the system, again you are basically, this mechanical work is tending to increase the internal energy of the system, as you can understand, because you are bringing the molecules closer, there may be more interactions, by forcing the atoms nearer, you can increase the interactions, or you can basically add to the internal energy, right? Increase internal energy. So in both cases, heat input as well as work done on the system, we are taking, means wherever internal energy is bound to increase, of the system is bound to increase. Say for example, if I am doing work on the system, or compressing the system for example, or I am adding heat to the system, I am exciting the molecules of the system, I am adding to the internal energy. So in such cases, we are telling that all of these are positive. So heat input to the system is positive, work done on the system is positive, while work done by the system against the external pressure is negative according to us, and heat rejected by the system to the surroundings is going to be negative, right? So basically Q is the heat. So if we have Q as the heat input to the closed system, and we have W, which is the mechanical work done on the closed system. Now, one very interesting thing that we will mention soon, that there are different types of systems, like this is closed and you have isolated. So there are various categories of system, or open. So we will define it shortly, but first let us restate first law in a simple math form. So you have Q that is entering, and we are assuming heat input to the system is positive, work done on the system is positive, work done can be mechanical work, it can be chemical work, or some other form of work. And then with all of these things that come in, what happens is your system was in an initial internal energy of Ui, it has changed to Uf, and you, as I told you, that internal energy before is Ui, and means at a reference configuration is Ui, and after addition of heat and work, it has become, say for example, Uf. Then the change in internal energy is what matters the most, and change is delta U, and delta U is nothing but Q plus W according to, and it's a closed system, so delta equal to Q plus W is the principle, is according to the principle of conservation of energy, or according to first law. Now, if the system, say for example, the system is moving and the system has some position or some special position in a potential field, I can also add all of those. So we can think of like Q plus delta U equals to Q plus W, and delta U is like changing internal energy, but we can think of also adding changing potential energy, changing kinetic energy and stuff. But we are basically considering a closed system where delta U, which is the change in internal energy, is equated to Q, that is the heat input to the system, and W, and both of them we have assumed to be positive. But it does not really matter. So this is what I just was about to say. Whatever sign convention you use, if you are consistent, it does not really matter. The relations do not change, right? It is not, yeah. So the infinite similar differential form is where it becomes interesting. Now, as you can see, du I defined as an exact. So du, so d, when I am using d, so I am telling that this is the total differential. du is the exact differential. However, heat input or heat transfer or work done, generally basically these are basically path dependent functions like work amount, the work done or heat input. These are all path dependent functions. So as a result, delta Q and delta W, we are using delta. See, we are not using D, but we are using delta. This denotes inexact differential where the integral depends on the path taken. See, in this case, the integral is path independent, right? We could just integrate like this, du I to f, and that was like uf minus u, right? But here you cannot. It depends on the path taken, right? We will give an example of that. For example, if I tell that there is a function z or z of x and y such that dz is an exact differential. That means integration of dz does not care about the path that has been taken, right? And let us assume that zxy is nothing but x times y, and we have this as the y-axis and this is the x-axis, and I am plotting, say I have the value of x and y to be 0, 0, and I have gone to somewhere like 2, 2, right? 0, 0 to 2, 2, and the value of zxy is x times y, right? Now I have taken different paths, right? I have taken different paths to go from 0 to 0, 0, 0, right? This 0, 0 coordinate is the origin to 2, 2. Say for example, I have taken a path like I go from 0, 0 to 2, 0, then from 2, 0 I go to 2, 2. Here I have taken a path like this, right? A curvilinear path, right? It's almost like a sine wave type of a sine or cosine wave type of path. Again, I have taken another path which is just like directly going from 0, 0 to 2. So 3 paths I have delimited. One is this one is this one, and the other one is like this, one is like this, and the other one is like this, right? All these 3 paths are there. But what I told, the initial point was 0, 0, and here is 2, 2, and we are telling dz. So dz basically is dxy, right? So dz is, but because zxy equals to xy, so dxy means y dx plus x dy. Now I want to know, so if I know dz, I want to integrate dz, right? I want to find delta z, that is change in z. This is the delta z. Delta z is nothing but integral of dz from 0, 0, that is the initial step, to the final step, which is 2. Now you see, z is nothing but xy, so I can write dxy, which is coming from 0, 0 to 2, 2, and that means I am just using xy and I am putting the limits, and the limits are basically the initial position and the final position, 0, 0 and 2, 2, and this becomes 2 times 2 minus 0 times 0, which is equal to 4. So dz is a total or exact differential. So you can see that whatever path has been taken, when I did the integral of dz, I just looked at the initial position and the final position. I did not look at whatever path was taken to achieve this final position from starting from 0, 0, right? And so whatever be the position taken, as you can see, delta z just depends on the initial and the final states, and we got an answer to be 4. Now look at an inexact differential. Let us assume that we have an inexact differential which is given by delta w equals to y dx. So again you have this coordinate system y versus x, and now delta w I have given as y dx. Now you see I have asked 2 paths. One path is like when going from here to here directly along the diagonal, and another path is like I go from 0, 0 to 2, 0, and from 2, 0 I go to 2, 2, right? Now if you see, when I go from 0, 0 to 2, 0, my equation is y equal to 0, and when I am going from 2, 0 to 2, 2, my equation is x equal to 2, right? Now, so this is the blue path, and this is say for example the yellow or diagonal path. So this delta W in the first path, in this along this path, if I have to find out delta W, the delta W is the amount of work done, or means it can be like delta W is nothing but the integral of delta W is nothing but integral of delta W. And there I am again giving some, these are my initial and this is my final products. Now this is what I have written. Now delta W is y dx, so I will write y dx, and it is going from 0 0 to 2 2. Now y is nothing but, in the first case, when I am going along a diagonal, the equation is y equal to x, right? So instead of y I have put x, and this becomes x dx, and now the x values are 0 and 2, so I just keep 0 and 2, and x dx is x square by 2, and 2 to and 0 to 2 I put the limits, and I get a value of, right. Now let us look at the blue part. So I go from 0 0 to 2 0, from 2 0 I go to 2 2, and now I am looking at finding delta W, which is again integral of this small delta W, right? This is the uppercase, and this is the lowercase delta, right? So you have this triangular delta, and then you have this delta here. This is the small delta. So if I have that, now I am integrating. So I have to integrate along the path, right? So I go from 0 0 to 2 0. Now 0 0 to 2 0. What is the equation? Y equal to 0, and I put y equal to 0 here. So this integral, this value is 0. Now I go from 2 0 to 2 2. Now in this case the equation is x equal to 2, whatever with the value of y, x equal to 2. So if x equal to 2, that means dx is constant. So right, if x equal to 2, then dx is constant, right? And so this value also goes to 0, right? So you have 0 plus 0, which is 0. So in one case you got a value of 2 when you are traveling along the diagonal. In the other case, when you took another path, we get a value of 0, right? So basically this is an inexact differential. This is an example of an inexact differential where the integral of this inexact differential depends on the path taken, right? So that's the idea. Now as I have told before, that there is this universe, and this universe is basically the system, that is the system that we are focusing on, that the body of matter. The system is this body of matter which is the focus of our study, and this is everything else. Everything else means everything other than the system. Now I could have made it as big as possible, but I have kept it small enough so that what I am telling is, this is my system. This everything other than the system that is influenced by the changes in the system. If the system is changing because of some process, then what is the region of influence, and that region of influence the surrounding, and together it forms the universe. This is something that we are clear. And we also talked about there is a boundary between the system and the surrounding, which you can call wall or a boundary, and this boundary's property determines how heat transfer will take place from system surrounding, or how work transfer will take place, various works transfer will take place from system to surroundings, right? Whether it's a chemical work, whether it's a mechanical work, how will it take place is based on the property of the wall that separates the system from the surroundings, right? So this we already know, that the region outside the system that is influenced or affected by thermal changes occurring inside the system is called the surrounding, right? And this boundary or wall, so that is the, I told you, that is one of the most important things to consider, because this wall and the boundary basically will give you the physics of the process, right? It separates the system from the surroundings, and for the state of a system, we know it is the condition of the thermodynamic system at the time of observation, which is described using a set of thermodynamic properties, right? The state of a system can be given by a set of thermodynamic properties. For example, I can give the state of a system in terms of U, which is the energy, then V, which is the volume, and mole number of different species like Na, B, C. These are basically A, B, C are the components, right? A, B, C are the components that are there in the system. So all of these thermodynamic properties basically describe the condition of a thermodynamic system at the time of expansion.